I welcome you all in this lecture of the vector integration. Today I am going to start my new topic, which is your surface integral. A surface integral is basically an integral which is evaluated through a surface. So let us define this surface integral. An integral which is evaluated over a surface is called surface integral, is known as a surface integral. Let f p be the continuous vector point function and consider an elementary area ds, which is basically n cap into ds, where your n cap is the outward normal to this elementary area. So if your f be the continuous vector point function and ds be the elementary area where your n cap is the outward unit normal, then the surface integral is defined as the surface integral is given by double integral over the surface S f dot ds, and it is same as surface integral over S f dot n ds. So this double integral is known as surface integral. Now, so say this is your x-axis, this is your y-axis, and say this is your z-axis, and let us draw this elementary area. So let us draw this elementary area. Okay. Suppose that this is your elementary area ds, and the unit normal to this elementary area is your n cap, and the normal vector to this y-z plane will be this k cap. So say this is your k cap parallel to this z-axis, and the normal to this surface is your n cap, and say this is your elementary area ds. Now the projection, orthogonal projection of this elementary area ds is your plane r. This will be your dx, and this is your dy. Let us assume that your r, that is this plane, let r is the orthogonal projection of this ds to r is the orthogonal projection of this elementary area to ds, which is your basically dx into dy. suppose that your R is the orthogonal projection of this elementary area ds to dx into dy in xy plane. So if this is your projection of this plane to this plane, then hence we can write dx into dy equal to ds into cos gamma. Now what is cos gamma? Now your gamma will be the angle between the planes of ds and dx and dy, where your gamma is the angle between ds and xy plane. Your gamma is the angle between plane ds and xy plane. Now the normal vector to this ds is your n cap and normal vector to this xy plane is k cap. So that means your gamma will be the angle between n cap and k cap, and n cap is the outward normal to your ds and k cap is the outward normal is the normal to the plane xy. Hence your gamma is the angle between n cap and k cap. Now if it is so we have cos gamma equal to, now your a dot b will be your a dot b is equal to modulus of a into modulus of b into cos theta. So this will be your basically n dot k, as the modulus of n and k is 1. So your cos gamma is n dot k cap upon modulus of n into modulus of k. So this is equal to n dot into k dot. Now let us put the value of this cos gamma here. So we have ds equal to, therefore your ds is equal to dx into dy upon n dot k. Just write modulus sign to neglect the negative sign. So your cos gamma is equal to dx into dy upon n dot k, and modulus is taken to remove the negative sign. So we have the value of ds. So therefore this surface integral is equal to the double integral over r f dot n. Now the ds is dx into dy upon n dot k. Now if your normal is same as, if your normal to the plane xy is same as your outward normal, then this n dot k will become 1 and the elementary area ds will be just dx and dy. So for a curve, our ds will be just dx into dy. So this is when we have taken the projection of r on the xy plane. When we have taken the projection of ds on the xy plane. Now if you take the projection of ds in yz plane, then this will be your, and again this is your r f dot n dy dz upon n dot I, and then again it is equal to double integral over r f dot n, then we have dx into dz upon n dot g. So this is the double integral of the vector point function f over a surface S, and this is also known as, this surface integral is also known as flux of f over this surface S. Now let us solve few questions based on this surface integral. So first question is, to evaluate. So our question is to evaluate the double integral f dot n ds, where our f is equal to zi plus xj minus 3 y square zk, and S is the surface of the cylinder, where S is the surface of the cylinder x square plus y square equal to 16 included in first obtained by the planes z equal to 0 to z equal to 5. So here we have to evaluate this double integral, where our surface is where your surface S is the surface of the cylinder x square plus y square equal to 16 included in the first obtained by z equal to 0 to z equal to 5. Okay, now let us draw this cylinder. So solution, say this is your y axis, say this is your z axis, and say this is your x axis. Now we have the circle in your xy plane, so this will be your like this. Then okay, again we have this plane. Okay, now your required region will be, here you can see that this is your x square plus y square equal to 16. As we have to evaluate this double integral for the region which is included in this first octane. Now for this part, okay, now we have to find out this double integral when your z is 0 to 5. So here we have z equal to 0 to z equal to 5. So this point may be your z equal to 5. This line is your z equal to 5. Here we have z equal to 0. Then we have, if you put y equal to 0, then this will be your x equal to 4. And now for the value of y, we have under root 16 minus x square. So if you take the horizontal strip, then if you take the vertical strip, then you will have the value of y as under root 16 minus x square. Okay, so here we have to evaluate this double integral in the first octane, for which we have the values of z from 0 to z equal to 5, and then which is included in your first octane. So let us find out the value of f dot n. So your n, your scalar point function phi will be equal to x square plus y square minus 16. So your grad phi, the differentiation of this function with respect to x and y, your grad is I del upon del x plus j del upon del y, and at outside we have x square plus y square minus 16. So this is equal to 2xi plus 2yj. Now your n cap will be grad phi upon modulus of grad phi. So now your grad phi is 2xi plus 2yj upon modulus of this grad phi. So this is your 4x square plus 4y square. Now your x square plus y square is equal to 16, so this will be your 64. So we have 2xi plus 2yj divided by square root of 64, so this is your 8. So this is equal to xi plus yj divided by 8. Now your f dot n is equal to, we have the value of n f as zi plus xj. So this will be equal to xz plus your yx, z dot j is 1. So we have divided by, this is your 4. 1 4. So we have the value of f dot n. Now here you can see that if you want to take x outside, then you can take it, and this is equal to your basically z plus y upon 4 into x. Okay, so this is your f dot n. Therefore this surface integral is equal to, now if you take the projection in the yz plane, then we have, now your f dot n is z plus y into x upon 4. Your ds will be, if you take the projection in the yz plane, then we have dy into dz upon n dot I. Now your n dot I will be, this is your n. If you want to take n dot I, then this will be your x upon 4. So this double integral z plus y into x upon 4, then we have dy into dz. Now your n dot I will be x upon 4. So we have this x upon 4, so it is cancelled. So here we have the double integral of z plus y into dy into dz. Now please note that here we have y equal to 0 to y equal to 4, and your z is from 0 to 5. So your limits will be, y will be from 0 to 4. As we have to calculate this double integral in the first octant, so for that your y will be from 0 to 4 and your z will be from 0 to 5. So our y is equal to 0 to 4 and our z equal to 0 to 5. So now if you integrate this term with respect to y, or if you want to integrate first with respect to z, then this is equal to, so the integration of z will be z square by 2, and then we have yj, and the limits of z will be from 0 to 5, and then we have dy. Now this will be your 25 upon 4, 25 upon 2. Now here we will have 5z, 5y. Now for the low limit we have the value 0. So now the integration with respect to y. So the integration of 25 upon 2 will be 25 upon 2 into y. Then here we will have 5y square upon 2, and then your limits from 0 to 4. So this is equal to 25 upon 2 into 4. Then we have 5 into 16 upon 2. So this is your 50, and then this is your 40, and the answer is 90. So the value of this double integral, when it is evaluated over the cylinder included in first octant, is equal to 90. Our next question is to evaluate the double integral where our f is x plus y square I minus 2xj plus 2yzk. So this is your f, and your s is the surface of the plane 2x plus y plus 2z equal to 6 in the first octant. Here we have to evaluate this double integral where our f is this function, this vector function, and your s is the surface of the plane. This is your plane which is included in the first octant. So solution. Now let us draw this plane. Say this is your y-axis, say this is your z-axis, and say this is your x-axis. So now let us take the orthogonal projection of this yz plane in the xy plane. So this will be like this. So this is your yz plane. Say this is your elementary area. This is your normal vector k, and the surface normal will be n cap. Now this projection is your in xy plane, where your x is from 0 to. If you want to guess the limit of x, then your x will be from 0 to 3. Here we have x, then here we have x at 0, y at 0, and z at 0. And at this point, your y will be 0 to 3. Okay. Now here we have to evaluate this double integral which is included in this first octant. So therefore, first of all let us find out the value of n cap. Your phi is this one. So your grad phi will be 2i plus j plus 2k. Your n cap will be grad phi upon mod of grad phi. So this is your 2i plus j plus 2k divided by, this will be 4 plus 5 plus 4, 9. So we have 3. So we have the value of n cap. Now your f dot n will be, your f dot n is equal to, so we have 2 by 3 into x plus y whole square, 2.3 into x plus y square. This is your f dot n. Then we have minus 2x upon 3. Then your k dot k will be 2yz upon 4yz upon 3. Then we have 4yz upon 3. Yes. So you can see that your minus 2x upon 3 plus 2x upon 3 is cancelled out. So if you take 2 by 3 common, then we have y square here, and here we would have 2yz. So you can see that the value of f dot n is in terms of yz. Now, and so this is your f dot n. Now let us calculate. So if you want to take the projection of yz plane in your xy plane, then your double integral f dot n into ds is equal to r. This will be 2.3 y square plus 2yz. Then we will have dx into dy upon n dot I. Now the value of n dot I will be your 2 by 3. So your 2 by 3 will get cancelled. So here we have 2 by 3 cancelled. So this is equal to double integral over r, then y square plus 2yz dx into dy. Now here we have to remove this z. So the value of 2z is 6 minus y minus 2x. So this is equal to y square y. Now the value of 2z will be 6 minus 2x minus y, and then the integration of this vector x into y, and this is your double integral r. Now this minus y square plus y square will get cancelled, so we have y into 6 minus 2x into dx dy. Now what about the limits? In this octane, your x will be from 0 to 3 and your y, if you take this straight, then you can say that your y will be at this point we have z equal to 0. So we have 2x plus y equal to 6. So your y will be from 0 to 6 minus 2x. So this double integral is equal to your x will be from 0 to 3, your y will be from 0 to 6 minus 2x, then we have y into 6 minus 2x into dx dy. Now the integration with respect to y will be your y square by 2, so we have 1 by 2, your x equal to 0 to 3, then we have 6 minus 2x whole cube into dx. Now the integration with respect to x will give you 6 minus 2x power 4 upon 4 into minus 2, and then we have the limits from x equal to 0 to x equal to 3. Now if you put x equal to 3, then this upper limit is 0. Now for x lower limit, we have x equal to 0, so this will be your 1 upon 16. Then if you put x equal to 0, then we have this 6 power 4. So this is equal to 36 into 36. Now you can cancel, so this will be your 4 9 are 36, and again this will be 9. So this value is equal to 81. So the value of this double integral is equal to 81 when your S is the surface of the plane which is included in the first octane. Then our next question is to evaluate this double integral where your f is equal to yzi plus zxj plus xyk, and S is the surface of the sphere x square plus y square plus z square equal to 1 in the first octane. So here we have to evaluate this double integral when your S is the surface which is included in the first octane. Let us solve it. So solution, say this is your surface and say this is your y axis, say this is your z axis, and say this is your x axis. Okay, now let us consider this as the circle. This is your part of the sphere which is included in the first octane. Now for this part, you can see that your x will be from 0 to a and your y will be from 0 to, this right hand side is your a square, not a, not 1. And now this will be your circle x square plus y square equal to a square. As we have to evaluate the value of this double integral over the positive octane, so your x will vary from 0 to a and your y will vary from 0 to under root a square minus x square. Now your phi will be x square plus y square plus z square minus a square. Your grade phi 2xi plus 2yj plus 2zk. Your n cap will be equal to 2xi, your grade phi upon modulus of grade phi. So this is equal to 2xi plus 2yj plus 2zk upon 4 x square plus y square plus z square. And your x square plus y square plus z square is your a square. So this will be your equal to, so therefore your n cap is equal to x I cap plus yj cap plus zk cap upon a. So we have this a. So therefore the double integral, again your f dot n is equal to your f is yzi. So this will be your f dot n will be your xyz. Then here we have xyz. Then again we have xyz. So if you want to evaluate this f dot n, then this will be your 3xyz upon a. So the value of this double integral is equal to, just take the projection of this yz plane in xy plane. So we have 3xyz upon a now into dx dy upon n dot k, and your n dot k will be equal to 3xyz upon a into dx into dy upon your n dot into k. Your n dot into k will be your z upon a. So this z upon a will get cancelled. So we have 3. Now the limits of x will be from 0 to a, and the limit of y will be from 0 to the square root of a square minus x square. Then we have xy dx dy. Now let us integrate first with respect to y. So the integration with respect to y will give you y square upon 2. So this will be a 3 upon 2. Then we have integral 0 to a. Now y square upon 2, and this square means a square minus x square into dx. Then we have x equal to 0 to a, your x into a square minus x cube into dx. Now the integration of x will be your x square by 2. So we have a square by 2 into a square. Then here we have a cube power 4 upon 4. Okay. Now this is equal to, now this is your a power 4 upon 2. So this will be basically equal to 3.2. Then we have a power 4 upon 4. So this is equal to 3a power 4 upon 8. Now let us discuss the volume integral, and then we will prove the Gauss Divergence Theorem. An integral which is evaluated over a volume, say, is called volume integral. Now if, say, V is the volume bounded by a surface S, then this triple integral V f dv, or this triple integral phi dv, are known as volume integral. Here your f is the vector point function and your phi is the scalar point function. Now we have a very important theorem based on this surface and volume integral, which is your Gauss Divergence Theorem. So let f be the continuous vector point function having partial derivatives and suppose that let V is the volume bounded by a surface S, then your surface integral f dot n ds is equal to the volume integral divergent f d. So the important application of this chapter, or we have an important theorem, Gauss Divergence Theorem, which says that your surface integral f dot n ds is equal to the volume integral of divergent f into dy. So if there is any difficulty in evaluating the surface integral, then we can evaluate those surface integral with the help of this volume integral. Now let us prove this theorem. So proof. So before proceeding, let us write its Cartesian component. Let us write this theorem in Cartesian form. So if your n is the normal to the surface, then if n cap is the normal to the surface S, then we can write n cap as I into cos alpha, j into cos beta, and k into cos gamma, where your I, j, k are the direction quotients. And let your f is equal to f1i plus f2j plus f3k. Then your divergence f will be equal to del f1 upon del x, del f2 upon del y, then del f3 upon del z. So therefore, your surface integral is equal to, now your surface integral, your f dot n will be f1 cos alpha plus f2 cos beta plus f3 cos gamma into ds is equal to this volume integral del f1 upon del x plus del f2 upon del y, then del f3 upon del z into dx, dy, dz. So this is the Cartesian form of this Gauss Divergence Theorem. Okay, now let us evaluate this right hand side, and we will show that this right hand side is same as the left hand side. So say this is your x-axis, say this is your y-axis, and say this is your z-axis, and consider a surface S. Say this is your surface S, and say this is your plane section of this surface, and say the upper part of this, say this is your circle, and say this is your upper half. This, if you assume this surface as a sphere, then this is the plane section of this sphere, which is your circle. Say this is your upper half of the surface, say this is your S2, and say this is your lower half of the sphere, lower half of the surface. So if this is your upper half of the sphere or surface, then let us take its projection. So this is equal to, then we have this plane. Okay. Say this is your S2, and the elementary area of this surface is your ds2. This is your surface S2, and suppose that the unit normal to this surface is your n2 cap, and your normal to this surface is your k cap, which is your normal to this xy plane. And again consider an elementary area of this, say this is your S1 surface, consider an elementary area, say this is your, say this is your ds1. So this is your ds1, and the unit normal to this ds1 is your, say, n1 cap, and again the outer normal is your k cap. Now here we will take the projection of this ds2 in your xy plane. Again, suppose that here the value of z is equal to say f2xy, and for this part your value of z is equal to say f1xy. So this is your z equal to f1xy, and here we have z equal to f2xy. So this is your plane R. Now let us evaluate the third term, which is your volume integral del f3 upon del z into dx, dy, dz. Now if you integrate this integral with respect to z, then this will be your equal to the, if you take the projection, then this will be your double integral. Then we can take f1. Now the value of your z will be from f1 to f2. Then we have del f3 upon del z and dz with respect to x and y. Now this integration will be your some function. Say this function is your, now the integration of this function will be your say f3. Now the value of f3 for your z equal to f2 will be equal to f3 xy z. Z is your f2 minus f3 xy f1, and here outside we have dx to dy. Now let's guess the value of this double integral xy f2 dx dy. Then this double integral f3 xy f1 dx dy. So this is equation number 2, or just write it as 1. So this is your equation number 1. Now let us evaluate the value of this f3 xy f2 dx dy. Okay, now here you can see that your R was basically the projection of ds2 or ds1 in the xy plane. So with the help of this, we can have the value of this double integral. Your dx, say this is your dy, and say this is your dx. Now here your dx into dy will be the projection of ds2 or ds1 in the xy plane. Again, your dx into dy is equal to projection of ds2 in xy plane. So if this is your projection, then this is equal to, now the value of this ds2 will be cos gamma 2 into ds2. I have already discussed in earlier that this projection is equal to your cos gamma into ds. Now where your gamma 2 is the acute angle between your outward normal N2 and the xy plane, where gamma 2 is the acute angle between ds2 and xy plane. Also your dx dy, now let us find out the projection of this s1 in the xy plane. So your dx dy will be projection of ds1 in xy plane, and this will be your minus cos gamma into ds1. Minus sign is taken because your gamma 1 is the obtuse angle between ds1 and xy plane. So we have the value of dx dy for both the integrals, therefore by 1, hence by 1 your triple integral, your double integral R f3 xy f2 dx dy minus R f3 x of y f1 dx dy is equal to double integral R f3. Now the value of dx into dy is your cos gamma 2 into ds2. Then here we have plus sign, and this is equal to your f3. And again your cos gamma 2 will be, gamma 2 is the angle between ds2 and xy plane, which is same as the angle between n2 and the normal to this ds2 is n2, and the normal to this xy plane is your k cap. So this is your same as cos gamma 2 is same as n2 into k into ds2, and again it is same as minus n1 into k cap into ds1. So this is equal to f3 into n2 dot k cap. Then we have ds2, and here we have minus minus plus. This will be your double integral over r. Then this is your f3. Then we have n1 dot k cap into ds1. So if you take this f3 k cap common, then in the bracket we will have n1 dot, we have n1 plus n2, so we can write it as the value over r, then f3, and here we have f3. So n1 plus n2 will be, say, your normal vector n. So we have k n cos. Then we have ds1 plus ds2. Say this is your ds. So the value is equal to f3 k dot n ds. And as the angle between your k and n is your cos gamma, so we can write it again as f3 cos gamma into ds. So the first term is, so the value of this third part is f3 cos gamma into ds. Similarly, if you take the projection of xy plane or the projection of yz plane, then we have the values of the remaining two terms. Also, similarly, we have this triple integral f3 del f3 upon del x dx dy dz as equal to over surface S. This is your now surface, this is your R, and here we have the surface S. So this is your f3, and now the angle between yz plane will be your cos. Now this is your cos gamma. Then we have cos alpha into ds. Then we have the integral. Then we have the triple integral del f3 upon del y dx dy dz equal to the surface integral f3 cos beta into ds. So we have the value of all the triple integrals. So now this triple integral will give you thus. Therefore, if you add these three integrals, so this is your equation number 2, equation number 3, equation number 4. Now, if you add all these three equations by 3, 2, 3 and 4, we have the sum of this triple integral as equal to the surface integral f3 cos alpha plus f3 cos beta plus f3 cos gamma ds, and this was your required result. Also, we can write it as, this right hand side can also be written as your cos alpha will be n dot I. So we have f3 n dot I into dx dy. Or if you want to write it as ds, then you can write. Then here we have n dot j into ds. Then we have n dot k into ds. So now this is your divergent f. This is your dv. So therefore, this divergent f dv, this is the proof for the Cartesian part. And now in the right hand side, if you take n cap common, then in the bracket we will have this is your f3, this will be your f1, and this will be your f2. This is your f1, and here we have f2. So this is your f1 cos alpha, f2 cos beta, f3 cos gamma. So f1, f2, f3. Now you can see that here we will have f1i plus f2j plus f3k. So this is your vector f. So this is equal to vector f. Then we have n cap. So n cap, and then at our side we have ds. So this triple integral divergent f dv is equal to the surface integral f dot n ds, and this is your Gauss Divergence Theorem. Now in the next lecture I will give you question based on this Gauss Divergence Theorem. Thank you so much for joining this lecture.